Hello physicists, in this video we're going to be going over Newton's second law, and possibly the most important of Newton's laws in terms of practical application. Newton's second law states that a system, which is basically your object an object of constant mass, okay, which we can assume is true, an object of constant mass m subjected to a totality of individual forces whose vector sum is sigma f. So an object of mass m, when subjected to some net force, experiences some acceleration that is inversely proportional to the mass m of the system, as n is in the same direction as the net force. That means if your net force is this way, then your acceleration will also point in the same direction as net force. If your net force is to the left, then your acceleration points that way. And what the second law states is that the acceleration is inversely proportional to the mass and directly proportional to, and is proportional to the net force. So basically, the acceleration is the net force over the mass. Or we get the familiar expression F equals ma, or sigma F equals ma. If you use this way of writing it, net force is equal to the mass times acceleration. And this equation is so incredibly important because now we can directly relate numerical quantities. It is an equation. It's an equation. So if I had a ball of mass m is 5 kilograms, and I'm pulling it on a straight line with a net force, just one force, force of 200, well, we see mass is kilograms, acceleration is meters per second squared, so with a force of 200 kilogram meters per second squared. And the unit kilogram meters per second squared is used so much that it has a special unit, the Newton, again named after Isaac Newton. 200 newtons. So a Newton is a kilogram meters per second squared. So we measure forces in newtons. That's the SI unit. So a force of 200 newtons. What is our acceleration? Now this is trivial because there's only one force. Acceleration is equal to the net force over the mass. Well, the net force is 200 newtons, and if we define this as the I direction, over 5 kilograms, we get 40 meters per second squared in the I direction. So the acceleration is also rightward, which lines up with our equation. Which lines up with our equation. So we have 40 meters per second squared. So our ball will accelerate at 40 meters per second squared in the I direction, so rightward. See, that was very trivial. Most problems are not as simple. Let's look at this one. Let's make it a little harder. Let's say you have a box. So one person is pulling it at a force of 300 newtons to the right. Another person is pulling it at 100 newtons. That makes an angle of 40 degrees, as shown right here. Okay, actually, let's make this 50 degrees. Looks more 50 degrees. So we have two forces, and this is our mass M. Our mass M is 30 kilograms. Now what's the acceleration of the object? What's the acceleration? What is it? Now, more specifically, what's the acceleration and also what's the magnitude of the acceleration? Now, in situations like this one, we use components. Okay, we use the same component strategy we use in the projectile motion problems by dividing each vector into components and then taking those parts independently. Okay, so we know that F1 is directly pointing to the right. Okay, so in the x direction, our acceleration in the x direction will be the net force in the x direction over m. However, we have this force, but we also have this force. Remember, this angled force has two components. One pointing this way on the left and one pointing straight up. So the one pointing to the left contributes to this x net force. Okay, because it's trying to pull back and act against F1. So we have 300 newtons. 300 newtons minus, because it's pointing to the left, 100 newtons times the cosine of 50. Cosine of 50. All that over 30 kilograms. So we have 300 minus 100 cosine of 50. We have 235.7, so to the right, which means it still accelerates to the right, and we divide by 30, and we get 7.86 meters per second squared to the right. Note that if F2 had been larger, then at some point it would accelerate to the left. It would accelerate to the left. So we know that it accelerates to the right. What about AY? Well, that's the sum of all the forces in the y direction, the net force in the y direction. But there's only one force acting in the y direction. That's this component. And note that this component's not really a force, but because F2 is angled, part of it is pulling the mass in a vertical direction. So we have to take that into account. And we take that part of F2 that's pulling it vertically and we represent it as a component of F2. Okay, so while the blue and red forces don't technically exist, they're the parts of the real force F2 that is pulling the object upwards. So that is equal to 100 newtons times the sine of 50. That's just the vertical component. Over 30 kilograms. So we get 100 times sine of 50. We get 2.55 meters per second squared in the upward direction. So our total acceleration is 7.86 if you were to write in IJ notation, 7.86 meters per second squared I plus 2.55 meters per second squared J. Okay, and that will sort of look like, so this is the I part, the J part. So you can expect that this will be about your acceleration. It'll accelerate like sort of this way. It'll accelerate sort of this way. And that's basically it. So when we finished the intro to Newton's laws, by covering Newton's third law, then we'll get into the real problems and introduce all sorts of special forces that will contribute to our understanding of dynamics, which is the study of forces and how things move. So after we introduce the third law, then we're gonna really analyze how objects move. Thanks for watching. See you next time.